Yoni, thank you. Yoni studied astronomy at the University of Maryland, and after graduating, spent several years at NASA Goddard working on transmission spectroscopy of exoplanets. He then returned to graduate school and the exoplanet group at Kansas. His talk tonight is entitled The Invisible Sky with JWST. Please welcome Yoni Brande.
Thanks, Kevin, for that very kind introduction. I hope everyone can hear me, but is it hello? Yeah. I'll try to project as much as I can here. But yeah, thank you, Kevin, for the kind introduction. What qualifies me as a subject matter expert for the Webb community events here is that I signed up for it while I was working at NASA. And luckily, I actually did some work on preparing for the imminent launch of James Webb, doing some simulations of observations. And actually, it might be easier. Okay. Now can people hear me? Okay, cool. Yeah, so I was working on simulations of particular observations with the observatory before it launches. And now that it's a couple years after I sort of finished that project, it's really exciting to actually see this come to fruition imminently. So fingers crossed here. So let me. Oh, come on. All right, I'm just gonna do this. Cool. So, oh, please. I'm assuming this is working now. All right. So as you might know, astronomy is one of the oldest sciences and possibly might be the oldest science, depending on who you ask. But until relatively recently, we were restricted entirely to naked eye observations. People would go outside and they would look at the night sky, and they would sort of remember in their heads or write things down how bright stars were and where they were and how things changed over long periods of time. But for several thousand years, this was not a precision science. This was really more of an art than anything, and was infused with quite a bit of mysticism and religious feeling. And then only in the last couple hundred years were we able to manufacture instruments that were precise enough to actually identify the brightnesses of stars and the positions of stars and the positions of other deep sky objects, and actually start to make scientific mathematical advances in our understanding of how the universe actually works. And this has been extremely motivating for humanity for thousands of years. And it's a major goal of the field right now to actually make sure that this continues to be an inspiring field, not just for those actually doing work in it, but for the public at large. So a little bit of basics on observing. I'm not exactly sure what everyone's background is here, and you may or may not be familiar with how astronomy is actually done. Quite simply, you look at the night sky with either your naked eye or some other assisting instrument. Here we have a diagram of a telescope where the astronomer is looking at a particular object, and this telescope collects and magnifies light such that this person can actually identify what they're looking at and its precise location. So you may be familiar with lensed telescopes or mirrored telescopes. So you can actually use lenses that actually refract light or mirrors that reflect light in order to focus our view of the night sky. But an issue is that as you want to make bigger and bigger instruments so that you get more sensitive, mirrors are basically your only choice because lenses tend to get large and heavy, and mirrors can actually be made as large as you want within reason, and actually be strong enough and reflective enough to conduct the observations you actually want to do. So on the ground, for example, we have reflecting telescopes that are up to 10 meters or 30 feet across. And just for comparison, at my house, I have a little reflecting telescope that is 90 millimeters across. So that's like 3.5 inches. And that's good enough to actually see quite a bit. But you can imagine that as you make these bigger instruments, they get more and more powerful. And as you go to space, you have fewer things to worry about, like the effect of the Earth's atmosphere on what you're actually observing. So here's a little diagram on some various wavelengths of light that astronomers actually look at. You can see in the middle here, we see visible light. So that's the things that you can actually see reflected all around you with your eyes. Just to the left of that in this plot, you see the infrared, which most of us actually experience as heat. If you stand outside on a hot day, the sun is actually heating you up through direct infrared radiation. And to the right here, you see the high energy stuff, things like ultraviolet. So if you are also standing outside on a hot day and it's clear enough, you could get a sunburn. So we sort of, as humans, act as astronomical detectors with our eyes, with our sense of feeling temperature, and also feeling pain after you get a sunburn. And you can imagine that if you build your cameras sensitive to these particular wavelengths of light, you can see all sorts of different things in the cosmos. So in particular, we're going to focus on the James Webb Space Telescope here, which is a 6.5 meter space telescope, primarily interested in infrared observing. So it is so much more powerful than you can see with your naked eye. And it's observing entirely in a band of light that you can't see with your naked eye, and actually, in fact, is not reachable from a lot of the ground. You can see that there's an opacity in the atmosphere on this plot for a particular wavelength. A lot of stuff in the infrared is actually not at all visible once you get out to particularly long infrared wavelengths. So as an astronomer, we sort of make two basic kinds of measurements. We want to see how bright something is, and we want to see what its position is. So after you make these measurements over some period of time, you can start to make inferences about what you're actually seeing and what physical processes might be causing the effects that you're seeing. So you can imagine that on the left here, if you look at this cutout of an astronomical detector, if you counted up the pixel values in each of those little pixels in the image, in that little donut in the middle there, that's the flux from a star. And by counting up all of those pixel values, you can tell how bright the star is. And that might change over time. And you could use that to infer some sort of physical law on whether the star is variable, or whether there's some obscuring gas or dust in between you and the star. But this brightness measurement is kind of the most basic thing you can do. And then if you're able to actually observe this thing precisely enough, you can actually see their motion across the sky. And so I've just sort of attached a GIF here of the nearest highest proper motion star, Barnard's star. And you can see that over 20 years, it actually moves quite significantly across our field of view. And so by combining these kinds of things, we can actually make inferences about these objects in ways that let us predict the behavior of other objects in the future. And another thing we can do, including this brightness, these brightness measurements, is we can actually split light up into its constituent wavelengths, like we saw before. I'm not going to go into this too much, but suffice it to say, it's a spectrum of the sun, and you can see that it actually peaks in the visible. Otherwise, it wouldn't be very useful for us to be able to see things with. And you can also see that it's not smooth. There are actually spikes and troughs where things are absorbing or emitting light in those particular wavelengths. This allows us to actually get at the constituents of what's actually in the atmosphere of the sun. So these are sort of important things that we can do as astronomers to actually look at things, see what they're made of, see how they're changing over time, and inform our own models about how the universe works. So that's kind of the basics of astronomy. We like to do astronomy with big telescopes and with big instruments. And if you go to space, it removes a lot of the hassle of being on Earth. So you can imagine that in the last several decades, NASA has spent quite a bit of time and money doing these kinds of large astronomical facilities, especially ones that live in space. So the quote unquote great observatories, as they're called, Compton, Spitzer, Chandra, and Hubble, have basically been driving astronomy for the last 30 years or so. And most people are aware of Hubble and some of the amazing images it's brought down. Fewer people are familiar with Compton, Spitzer, and Chandra. But actually, if you combine the light from these various observatories, you can get stunning images like this. So you can see that this is an image of the Cassiopeia A supernova remnant. The blue and the green are X-ray images from Chandra. The gold is optical images from Hubble, and the red is infrared from Spitzer. And by combining all of this, we can actually see structure in this gas cloud that allows us to understand what exactly went on when the supernova exploded. And unfortunately, if we didn't have all of this capability, we wouldn't be able to do this kind of work. So it's incredibly important that two of these great observatories are no longer with us. Compton, which was the first to go, observed primarily in gamma rays. Spitzer only recently failed us. It ran out of coolant and fuel and is now sort of left adrift, but suffice it to say, we don't have an infrared telescope anymore. And so Chandra and Hubble are sort of the only ones left. And so Chandra is in X-rays, and Hubble observes a little bit in the ultraviolet, mostly in the optical, and a little bit in the near infrared. But we don't have a near, mid, and far infrared instrument like Spitzer anymore, which is important because the James Webb Space Telescope will step in to fill this gap. Hubble has a limited lifespan. Spitzer's gone. And it would be really nice if we had a big flagship observatory to sort of take over these big scientific capabilities while those observatories are no longer with us. So I just want to compare these a little bit. On the left, you can actually see Spitzer's mirror size scaled. I've scaled all of these to each other. And so in the middle, you can see Hubble's mirror size. So Spitzer has a 0.8 meter mirror. Hubble has a 2 point something meter mirror, 2.5, 2.4, and James Webb is 6.5 meters. So this is like 22, 24 feet across, basically like the size of that screen or bigger. And I've also sort of overlaid their wavelength bands that they're sensitive to, scaling the size of the bar with the size of the mirror. So you can see that Hubble actually overlaps just a little bit with James Webb in the near infrared. And James Webb sort of covers this near and mid infrared band that we don't have access to now that Spitzer's gone. And since Spitzer's gone, we actually don't have access to this far infrared band anymore. But there's quite a lot of science we can still do in these James Webb sensitive bands. So just to sort of show why we like to use the infrared, if you are sort of standing outside on a hazy, cloudy day, you probably can't see that far. Sometimes you can't hardly see your hand in front of your face. But if you've ever used one of those little infrared camera apps or modules that you can stick onto your smartphone and look and see your hand glowing red as opposed to some cool blue background, that is actually infrared radiation being emitted by your hand from the heat of your body. And so that is very useful because it can cut through a lot of that haze and dust that you might not be able to see through with your eyes on a cloudy day. And in space, we see these similar processes anyway. Here's an image of the pillars of creation in the Eagle Nebula. On the left is a famous Hubble optical image. And you can see that there's really interesting dust structure, and these pillars, come right out of the nebula. And you can see a couple of foreground stars, but there's really not a whole lot of star activity in this optical image. But on the right, if you look at the infrared, this is a Spitzer image of the same field, you can see hundreds and thousands of stars. And in particular, the ones that are inside the dust are bright enough that they're actually shining through the dust. The infrared wavelengths are are set up such that they can actually go right through the dust that gets blocked by the optical. And as you can see this, you can see that the pillars of creation are named quite aptly and intentionally by the people who made these images, because this is an intense star forming region. And if we were only observing in the optical, we would not be able to uncover this star formation at all. And so it's extremely important that we have this infrared capability that James Webb is going to return to us. And in another reason that we like using the infrared, you may be also familiar with a concept called the Doppler shift. If you're standing outside and an ambulance is going by, as it comes towards you, the siren sounds qualitatively different than as it passes you and as it goes away from you. This Doppler shift is common to all waves. So as something comes towards you, the wavelength, and in the case of an ambulance, the pitch of the siren actually gets compressed, so it sounds higher. And then as it passes you and moves away from you, the wavelength gets elongated and the pitch goes down. So you can see this weird distortion where something gets higher as it comes towards you, and then as it passes you, it sounds normal. And then as it goes away from you, it starts to sound more and more distorted low. And so this happens with wavelengths of light as well. And so you can see that on the top here, if we have a reference spectrum of some galaxy, it's in a particular place. And then on the bottom, if the galaxy is moving away from us at some speed, these spectral lines get shifted towards the red, towards the low energy side of the spectrum. And this is important because as things are further away from us, they tend to move faster. Hubble famously came up with Hubble's law, where he took spectra of various galaxies at various distances and noticed that the ones that were further away from us tended to be moving faster away from us. And from this, we eventually inferred the expansion of the universe and the Big Bang and everything like that. But an interesting side effect is that if you actually want to see things that happened very soon after the Big Bang, that is, they're very far away from us, 10, 12, 14 billion light years away, that means we're seeing them as they were 10, 12, 14 billion years ago. And so since they're so far away, they're moving very fast away from us. And so their spectra are redshifted quite significantly. And you actually have to go, you can't see them in the optical hardly at all. And you actually have to go to the infrared to learn much about the very early universe. So how is JWST actually going to do all of this observing? Over the last 15 years, they've been building this thing. It took the involvement of 3 separate space agencies, NASA, the European Space Agency, and the Canadian Space Agency. And there are literally hundreds of partner institutions, all the way from people building individual bolts that screw instruments together, up until massive state and national universities contributing scientific expertise to help this actually go. Here's a quick view of the spacecraft actually being assembled and tested at Goddard. This is the main mirror segments. When I was at Goddard, this had just shipped out. So I actually missed getting a cool selfie with the mirrors in the background, but a lot of my friends who were there before me did, and I'm very salty about that. But you can see that it's made of these hexagons, and each hexagon is 1.3 meters across. So 3-4 feet maybe. And so the whole array is 6.5 meters across. And these are not your normal mirrors. If you just use your normal mirrors that you might see in the bathroom, not only are those optically not good quality enough for this kind of work, glass and aluminum backing just doesn't work for the kinds of light that we actually want to see. So these mirror segments are made of beryllium, and they were machined in a very particular way for peak strength and lightness. And then they were coated with a very thin layer, like atoms thick, of gold. So this is a pure beryllium mirror with a gold backing. And it takes this kind of pristine optical coating to actually get the sensitivity you need in the infrared to actually see the kind of things we actually want to see. So it's not just a big mirror. There's a lot of cameras that actually go into this. So these are, this is the instrument module also being worked on at Goddard. And so you can see that there are several different thermally blanketed boxes here in this structure. I've kind of tried to label them. So this over here is near spec. Back here is nearest. Near cam is in the middle here. And on the left here is MIRI. And I'll explain what these acronyms are, but suffice it to say, we have 4 instruments on the observatory that allow us to see a wide part of the infrared spectrum and have widely different capabilities in the actual images that it can take. So in this case, NearCam, which is this one out here, was the first instrument they actually planned for this observatory. So it's the near infrared camera. It takes pictures at wavelengths under 5 microns. And this is sort of one of the main imaging instruments on the observatory. So this is the kind of thing that you're going to be able to use to actually look at things like the pillars of creation, looking through dust to see young stellar nurseries, and actually taking pictures really far back in cosmological time to see, the earliest galaxy structures. NearCam also has a couple of instruments called coronagraphs, which actually block out the light from a particular spot on the camera. And that'll let you image things that are not very bright, that are next to very bright things. So if you imagine a dust disk orbiting a star, the star is extremely bright and it'll totally outshine the dust. But if you actually want to see what the dust is like, then you block out the light with a coronagraph and you can actually take an image of the light coming off the dust directly. Behind, actually over here on near spec to the right here, it's another near infrared instrument, but it's a spectrometer. So it actually will be able to split the light up that it sees into its constituent parts from 1 to 5 microns. And this is going also to be able to observe lots of targets simultaneously. So you can actually do surveys of hundreds of stars with this instrument, or you could actually take an image of a galaxy that's several billion light years away and actually get spectra of different spots in the structure of the galaxy to figure out how that galaxy is actually evolving as time goes on. Nearest in the back here is a Canadian instrument. It also is combined with the guidance sensors of the observatory. So it's going to be doing science and it's going to be orienting the observatory, making sure that everything is precisely pointed. And its spectroscopic capabilities are primarily designed to target exoplanets as well as sort of this cosmological first light. And then over on the left here, MIRI, which is the instrument I'm most familiar with because I was working with simulating observations with it, is a lower resolution instrument, but has much broader wavelength coverage. So if all the other instruments are mostly under 5 microns, this goes from 5 to 28 microns. And this is sort of the capability that we lost entirely with Spitzer. And so it has imaging capabilities. It'll take a lot of really cool images. It has spectroscopic capabilities. It'll actually let us investigate the structures of lots of interesting objects. And it has coronagraphs, which will let us directly image exoplanets. So this is something that we can really only do with extremely large observatories on the ground right now, and is extremely competitive to actually do these kinds of observations. So I'm interested in that because that's what I was working on, and I think that this is extremely interesting capabilities enabled by the fact that this observatory is going to be cooled down to 30 degrees above absolute zero for all the near infrared instruments and 7 degrees above absolute zero for MIRI. And it does this entirely passively without any refrigerant at all. So hopefully we can actually get quite a few more years out of James Webb than we were able to out of Spitzer. And if it'll let me, I would like to play this. So here's a quick video from ESA on how they actually stow the observatory for transit to launch. So you can see that it's a really big spacecraft. The mirror is 6.5 meters across. The sun shield mirror the size of a telescope, and it actually folds up like an origami crane almost. It gets fit into this rocket, and the rocket's only 4 meters across, I think. And so you actually need to fold the entire observatory in on itself to actually launch it and get it into space. Yeah, cool. So that was a nice little video, but all of this just happened. it was a couple of months ago that they actually declared everything done and finished and packed up, and they shipped it off to French Guiana. And Monday or Tuesday, it actually got there. So all this is happening like right now. Actually, this is current stuff, and they're in the process of unloading the thing off of the ship and moving it to the actual assembly building to stick on the rocket. And then on December 18th, right before Christmas, they'll actually hit the button, and hopefully it'll actually go and launch. So let me see if I can advance here. Oh, no. No, don't do that. Oh, cool. Okay. So after it launches, it's actually going to go 1 million miles away out to a point called L2. And so L2 is what we call a Lagrange point. And it's a point of basically low fuel use. So it's a very stable orbiting point outside of the Earth's orbit compared to the sun. And this lets the observatory actually point its sun shield towards the sun constantly. And let me just pause it like out here. And so you can see that all of the optical stuff and all the instruments are here. And as that happens, that allows it to look away from the sun and keep everything cool so that you don't accidentally point the observatory towards the sun and ruin all of your nice science. So it's incredibly important that the spacecraft orbits over here because it costs very little fuel to maintain this orbit, and it's very thermally favorable towards the types of observations we actually want to make. And so over 6 months or so, it'll actually sweep out enough area in the sky that it can observe the entire celestial sphere. And there are 2 points, basically due north and due south, that it can always observe just by tilting towards or away from this anti-solar point a little bit. So let's see if it'll let me. And then once it gets out there, it actually needs to spend some time. I'm going to mute this. It actually needs to spend some time to align the mirrors. So you saw that these are all individual mirror segments sort of bolted onto a big dish to make a single mirror. These are adjustable on like the micron scale, basically allowing us to precisely focus the light from the telescope onto the instruments. And this is important because not only do these need to be properly aligned so we can actually see anything, it actually allows us to make very precise corrections to the light we see coming in. So if you're actually looking through some area of space that has stuff in it, gas, dust, whatever, the light that you actually see from that background object gets broken up a little bit by the gas that it's moving through. So we can actually make very precise corrections to the light incident on the observatory to make sure that we're actually getting the most precisely focused observations that we can. And this is something that we do on the ground, but these active correction capabilities haven't yet been demonstrated in space. So this is capability that we really think will be groundbreaking for the kinds of science that we actually want to do. So here's just a quick overview of some of the scientific goals that we actually want to use the observatory for. And I've alluded to some of these in the previous slides of the talk, but I'd like to go into detail here. So in particular, James Webb was designed to study the early universe. This is not something that we had the capability to do from space previously very well. Spitzer could do it because it could see in these mid-infrared and far-infrared bands as well, but it wasn't sensitive enough because it's not big. So James Webb, as the sort of biggest and baddest observatory in space, will actually be able to do a lot of really interesting science with this stuff. Here's just a quick diagram of basically the universe's structure as time goes on. So at the bottom, you can see the Big Bang, and at the top, you can see the observatory sort of looking back in time. So after the Big Bang happened, the universe was basically entirely filled with this hot, dense plasma. And it was so hot and it was so dense that it was totally opaque to light. And if you were standing there, you would get incinerated and you would die, but you also couldn't see anything. And so as the universe expanded and cooled, eventually this density dissipated enough and things cooled down enough that you could actually form hydrogen atoms from these primordial protons and primordial electrons. And as this happened, as you form this hydrogen atoms, all of these hydrogen atoms gave off this big flash of light, and this barrier of light basically uniformly illuminated the entire universe. And now, if you go to a very particular band pass called the microwaves, you can see this as the cosmic microwave background. And this ended up giving two sets of scientists Nobel Prize, one of which was John Mather, who's the project scientist for the James Webb Space Telescope. But this is basically as far back in the universe as we can see. There's nothing past that because this is the first light that you can actually see emitted in the universe. But now that the universe is transparent to light, the CMB sort of red shifts away, and you start to get other sort of normal matter that you can actually see with your eyes. And so enough primordial gas sort of coalesces around this matter. And so these dark matter structures start to form, and this ordinary baryonic matter structures start to form, and you start to form the first stars and the first galaxies. And so this sort of lights up the universe again and causes this, what we call this epoch of reionization. This epoch of reionization. And so this excited all of the hydrogen atoms in the universe again, which splits it back into protons and electrons, hence ionizing them. And so this structure is actually some of the earliest structure we'll be able to see with the James Webb Space Telescope. And as we sort of use JWST to observe how this reionized gas interacts with these other sources of light, the sort of proto-galaxies and early stars, we can actually study the characteristics of those stars in ways that we weren't previously able to do, because you can't see them directly. They're so faint and they're so redshifted, you can't actually see them. But you can see their effects on this reionized gas. And so one such program that'll actually be doing this sort of work is this one to investigate the Hubble tension from Friedman et al. It's a first cycle program, and what's it going to be doing is measuring the differences in the rates of expansion of these galaxies, these primordial galaxies, as they move away from us in various parts of the sky. And so a notable problem in cosmology has been that if you measure these rates of galaxy universe expansion, you get different values for what we call the Hubble constant, which, if you invert it, basically gives you the age of the universe. And so James Webb is actually big enough and sensitive enough to be able to observe these different distance scales and improve those estimates in a way that hopefully explains why these observed values are so different. And if we can actually pull this off, this would possibly remove the need to come up with new physics to actually explain how the universe came to be as it is today, or maybe we'll actually find out that those differences are robust, and people who are a lot smarter than me will need to do a lot more interesting theoretical cosmology to actually figure out what happened in the early universe to make these problems. So JWST will also be interested in galaxy evolution. We want to answer questions like, how do galaxies form, whether old galaxies are qualitatively different than recent galaxies. We want to know how galaxies and our black holes interact. We're interested in how galaxies merge and taking pictures of this really interesting complex structure, and we want to know how galaxies actually form stars. And so this actually was the one I was thinking of as far as reionization goes. There's another Cycle 1 proposal actually looking at these protoclusters of galaxies and how they interact with this primordial gas and actually reionizing it. And so the hypothesis is that these protoclusters, which are really good at forming stars because there's a lot of free gas in the universe, and things are basically all going off at the same time, these are probably really good sources for this reionization energy. And if you look at more recent galaxies, they should have different environments, and you should be able to make inferences on what a recent star-forming galaxy behaves compared to an ancient star-forming galaxy, and that should also give you more information on the conditions in the early universe. So we're also interested in the life cycles of stars themselves. Stars form out of clouds of gas and dust that sort of collapse in on themselves. We kind of want to know how those clouds form. It's nice to know that there's lots of these star-forming regions out there, but investigating the actual differences between them is very important, especially when you look at different groups of stars that form together. So we'd like to know whether these are related, the various populations of stars based on sort of what generation they are, if they're very early, as opposed to if they're very recent. As these stars live and are born and live and die, when they go supernova, they seed their environments with lots of heavy elements. We'd like to know whether that has an effect on whether these stars form planets. And then we'd also like to know what exactly happens after all of these stars die. So following that, there's a very good program on the Crab Nebula. So here's a very famous image of the Crab Nebula from Hubble. It was originally observed in 1054 CE by Chinese and Japanese astronomers, but it was rediscovered as the nebula we know today in the 18th century. And here's a program on actually looking at the imaging this and taking multi-object spectroscopy of it to actually map the dust very precisely in this nebula, and figuring out the ratios of the various elements that make up this gas and dust. And by doing that, by comparing this ratios to particular model predictions, it can actually, well, hopefully the idea is to determine the particular explosion mechanism that actually set this off, which has been a matter of some debate in the supernova community recently. So most interesting for me, because I work on exoplanets, is all of the various exoplanet James Webb proposals. I've restricted myself here to a single one. I could have gone basically the entire time just talking about the things that we're going to be doing with James Webb on exoplanets. But basically, we're interested in, as always, how these things form, how these things evolve, how to actually find them, what they're made of, understanding their environments, understanding their orbits. And to do this, we're basically going to be using all of the instruments on the observatory. And so here's just a view of a particular protoplanetary system. I don't think this is a specific target for the first cycle of James Webb, but you can imagine that if you're observing this with James Webb, you can actually see things like the structure of the disk and whether it's being perturbed by young planets that we can't directly see, and how this multi-star system actually interacts with itself and whether it has any implications for possible planet formation. But something we actually are going to do with James Webb is, for example, look for particular signals indicating the presence of geology and volcanism on alien planets. So this is actually one of two programs led by an advisor of mine, Laura Kreidberg. This planet is called LHS 3844b. It has an 11-hour orbit. It has a 1400 degree Fahrenheit surface temperature. It is very close to its host star. It is very tidally squished by its host star. And these are things that indicate to us that it may have either lava on its surface or lots of active volcanoes spewing out hot gas and molten rock. And if we use the instruments on James Webb very creatively, we can actually use this to search for evidence of volcanoes, both by taking images directly of light being emitted from the planet's surface as it goes around its host star, or by spectroscopically characterizing its atmosphere and looking for telltale gases that you would expect to see in volcanic emissions. And not to leave out the solar system, although certain people in the community don't always appreciate what we actually do in the solar system, because solar system science often gets done with direct probes. You can imagine all of the Mars rovers are very nice facilities to have when you can actually have a camera, look at a rock, pick it up, drill into it, see what it's made of, and sort of send all of that information back all within half an hour. We're very good at doing that, with these probe missions, with these rover missions. But big space telescopes are also very important for doing solar system science. So there's a lot of asteroids and near Earth objects that we either can't observe because they're too faint to see from the ground, or they're not in a place where you can actually see them from Earth. You can do lots of interesting science on Mars's atmosphere with big space-based observatories, looking at things like the giant planets, Jupiter, Saturn, Uranus, Neptune, and their moons. These are also big targets, especially since there are a lot of upcoming missions to these places in the future. And then things like in the outer solar system, comets and trans-Neptunian objects like Pluto and the Kuiper Belt, and all of these things that are too far away and too dark for us to see directly. James Webb will allow us to actually do lots of observing of these particular objects that we wouldn't have been able to do before. In particular, Saturn's moon Titan is the focus of one particularly exciting Cycle 1 proposal. Another advisor of mine, Connor Nixon, is leading this one. Titan is Saturn's largest moon. It's actually bigger than our moon. It's like the size of the planet Mercury. It has an extremely thick atmosphere, and it has a lot of clouds and hazes that we haven't quite been able to see through yet. So if you do high resolution spectroscopy with James Webb's instruments, you can actually map seasonal variations in this cloud cover based on different irradiations from the sun and different interactions with Saturn as Saturn actually orbits the sun and as Titan orbits Saturn. And this is incredibly relevant because the Dragonfly mission got selected just a few years ago, where they'll actually be sending a quadcopter drone to Titan to fly around in the really thick atmosphere and actually directly sample these gases and look at what's on the surface and play around in the environment on Saturn's moon. And that's coming up in the next decade and a half or so. So stay tuned. And it's not just science stuff. I mean, it's all science stuff, but it's not just stuff that's going to go into papers in obscure journals that no one's ever actually going to read. The actual development process of these big space missions always comes up with interesting spin-off technology. So in particular, all the stuff that went into wavefront control, all the stuff that went into the IR detectors, all the stuff that went into actually making sure that this thing can actually be launched and survive the launch trip up to L2. These are all very important processes that directly benefit us today. So I have extremely bad eyesight. I wear very strong contact lenses. And in the future, if it becomes cheap enough, I might like to get something like LASIK surgery so that I wouldn't have to deal with contacts and glasses in the future. So as it happens, all of the precision optics that were developed for JWST, the diagnostic tools that were used to make sure that the observatory is actually good to go for space observing is directly applicable to imaging somebody's misshapen cornea and actually reshaping it to give you good eyesight. So the process is exactly the same. And in this case, the improvements made for JWST optics testing have already been applied to improving things like eye surgery. In addition, the computers that actually run the observatory had a lot of good development in things like integrated circuits. And because these are really important, robust things to build for something that you're never going to be able to service, it's good that we were able to develop these to a point where they actually got used for the last Hubble servicing mission. So Hubble actually orbits just 250 miles up. And so while we had the space shuttle, they could send astronauts up, dock with the Hubble, and pull instruments out and stick new instruments in so that we can actually change the capabilities of the observatory with direct human input. And so computers that actually were designed to run James Webb are now running on Hubble. And it's incredibly important because just recently Hubble had a fault which knocked out the computers for several weeks. And as part of the recovery process, they switched over to the backups that were installed on this latest servicing mission that have this technology pedigree from James Webb development. So hopefully that'll allow us to use Hubble for years into the future. And if James Webb hadn't been in development, those might not have been in existence and we might have lost Hubble already. In addition, things like vibration testing for making sure that the observatory survives the rough conditions of a rocket launch. These are already being used, not specifically from James Webb, but the technology in general gets used to improve things like your car's suspension, testing road conditions for thousands of miles in these sort of auto development simulations. And the infrared sensors that were actually developed for James Webb had legacy from Spitzer and will continue to actually improve the next generation of space telescopes after James Webb launches and is finished in the next 10 years. And I just want to give a quick shout out to Vox's Unexplainable podcast. They put out 2 episodes recently covering a lot of the same material I did, but not in as much detail. But they actually got to talk to a lot of the James Webb scientists and some people actually running the programs. And so it's interesting to actually hear these people talk about their own science and make the case sort of on this in this public podcast form. So the September 22 and September 29th episodes are good overviews, and they should be basically anywhere you can find audio content. So I think that about covers it for what I wanted to talk about. So with that, I'll take questions. Blue sweater, I think I saw first. So fingers crossed, it's about a 6-month process. So it takes a while to get to L2 because it's 1 million miles away. And they have to do a lot of things in sequence very precisely, or else the whole thing is a wash. And $10 billion basically gets flushed down the toilet. So all of the folding and origami that they had to do to get it onto the rocket, that has to happen in reverse to actually deploy the telescope. And not only does it have to happen in reverse, if they get it wrong, let's say they open the mirror too far before the sun shield is fully deployed, that could totally toast all of the instruments if they can't get the orientation worked out from manual commanding on the ground. So they put a lot of work into actually rehearsing and making sure that these processes are going to happen properly in their proper order on the ground. And then as it happens in space, they're going to be doing things over the course of days and weeks and months. And then it'll actually be out there and they'll have to wait for a while for everything to cool down to the proper ambient temperature before the instruments are ready to use. Then there's some calibration images and blah, blah, blah. And basically at the end of 6 months, hopefully we'll be actually getting real science data from it. And there'll probably be some really interesting, quote unquote, first light image, and they'll take a picture of something possibly, safe to look at. So not something that's really challenging observation to make, but there should be a reasonably pretty picture coming down that they'll be sharing with everybody. Yeah. So this question is about prioritizing studies. It's a good question because I don't necessarily have a good answer for that because the one that I submitted didn't get selected. And I'm kind of sad about that. But what they're trying to do is they're trying to optimize the amount of time used with the realisticness of success in the scientific program being proposed. So JWST has a limited lifetime. It's not going to be up there forever. So they really want to pack as much science into the operations timeline as possible. So for example, I submitted a proposal to directly image some nearby planets that we knew existed, so it wasn't that risky. But as far as the actual optical needs of the observatory for making these pictures, they were actually pretty, they went up basically to just to the limit that I figured I could get away with. And so if you look at the list of science that actually got accepted, there's a very similar proposal to mine, except it's imaging a different planet in about half the time. So they want to make the trade-off between risk and reward and actually time spent, because it's going to cost something like $10,000 or $15,000 an hour just to run this thing. And that's what you get paid as an observer if you actually get your science selected. So these go through a big panel. They'll be taking submissions, I think, once a year, and then they split up all the submissions. They give them to panels of experts in the field, and then they sort of rank them based on scientific merit and risk and time. And so hopefully they pick the right ones, and we'll see how things work out in the first year. Over on left here. So with Spitzer, they were after the active coolant ran out. I don't remember the specifics on any sort of passive coolers, but they allowed the observatory to warm up to whatever the ambient was in that part of space, and then they were restricting themselves to using the IRAC instrument, which is at shorter wavelengths and is less affected by warmer temperatures. So with James Webb, there's actually active coolers on board, but they're not using refrigerant. They're using, I believe they're piezoelectric or something like that. They found a way to actually have mechanical cooling of the instruments, particularly MIRI, in order that they can actually get sensitivity in those wavelengths. For the near infrared instruments, they're really just relying on the big sun shield to reflect away as much sunlight as possible, so that the cold side of the observatory can get down to 30 Kelvin or so. But the active coolers will push MIRI down to 7 Kelvin, and I'm sure there are interesting overviews of how that actually works. Yeah. So this is a question about the temperature of Titan and whether that is actually good for infrared wavelengths. In general, all planets are basically best observed in the infrared. So if you can imagine looking at the picture of the spectrum that I showed, the spectrum of the sun, because the sun is 5,000 degrees Kelvin, 5,800 degrees Kelvin, it peaks in the visible light where we can actually see things. Planets are a lot cooler than that. They're normally less than 1,000 degrees. And often, if you look out to the gas giants like Jupiter and Saturn, they're less than 200 degrees Kelvin. And Titan is probably, I don't remember offhand, but it's probably in that 100-degree-ish or less range. So it's very cold by our personal standards, but that means that it radiates its peak wavelengths in the infrared. So if you actually are doing infrared science, you're seeing emission from the internal heat of the moon itself. And that gives you a lot better sensitivity for actually looking at the structure of the various layers in the atmosphere that you wouldn't be able to do if you were looking at it in the optical. So, yes. So yeah, so that's a question about the orientation of the observatory, which you can actually see here. Just for the purposes of like showing things, they always pick the optics pointing along one of these like keel axes. But really, that whole telescope superstructure can swivel behind the sun shield. So it can look up, it can look down, it can look left, it can look right, it can look straight out, and they can actually tilt the entire observatory a few degrees in any direction. So if you imagine just sort of looking in one direction, your peripheral vision is like, I don't know, 110 degrees or so. If you actually swivel your head, you can basically see, 180 degrees, possibly even a little further. So here, the field of regard is, I don't remember the exact field of view, but it's such that you can basically see out and in some cone, and that extends basically in all directions, not past the sun shield. So it actually does take several months of the orbit to actually sweep out enough of the sky that you can actually see it without accidentally running into the sun and toasting all the cameras, which would be bad. Back there. It's a year. So it's a million miles away, which sounds like a lot in the grand scheme of things. But if you compare the orbital distance of the Earth to the sun, that's 93 million miles. So that's still very, very specifically in the Earth's neighborhood. And so the point about L2 is that it's stable. And so it's stable in the way that if you look at it in a rotating frame of reference, you always see spacecraft at L2 stay at L2. And basically, because these Lagrange points orbit along with the Earth, they take a year to go around the sun, just like the Earth takes a year to go around the sun. Yeah.
One line of L2, is there some reason why it's always orbiting around?
Yeah, so you have to orbit around L2 because they're not perfectly stable, and because the way the math works out, the Lagrange points are only defined for two-body systems. So if you imagine the solar system with none of the other planets in it, and just the sun and just the Earth. So if that was the case, and the spacecraft itself didn't have any mass and everything else was idealized, you could basically sit at L2 perfectly and never need to spend any fuel to go where you needed to go. Unfortunately, we live in the real world, and there are lots of other planets and lots of other things going on, and gravitational waves and all these other things that actually make our idealized systems non-ideal. So in the real world, the best you can do is actually orbit around this stable point. And so the spacecraft has engines that will let it actually station keep near L2, but not exactly at L2, which is good because these Lagrange points are popular places to put all sorts of spacecraft. And so it'll actually be sharing, not sharing space directly, but there are other spacecraft there conducting operations. And it's nice to make sure that you have control of all of them independently so that they don't bump into each other. But yeah.
I also had a question about the infrared cooling.
Mhm.
Was the case long ago that was
I don't, if there wasn't if there was a liquid refrigerant on board, that was descoped a decade ago. I couldn't tell you exactly when that happened, but as it is, I believe the technology development needed to validate the passive cooler would have needed to have been completed a while ago. So I don't know when that was going to happen, but it wouldn't have been recently. In the back. Well, for one thing, they need to be cooled to an extremely low temperature because if they're at room temperature, they're going to be emitting their own infrared wavelength. And so if you can imagine it, if you're looking at your hand, which is say 85 degrees Fahrenheit, with an infrared camera, you can't see anything behind it that's cooler than 85 degrees. So if you have your cameras trying to take the picture that are, warm comparatively to the kinds of things you're trying to look at, any infrared interference from the camera is going to degrade your observations. That being said, the sun shield, if you didn't have the sun shield, all of the incident radiation from the sun would just directly be heating up the structure of the spacecraft. And because there's nothing else in space to block it, it would heat up really quickly and you would get to like several hundred degrees Fahrenheit with no way to cool it back down. So the sun shield is really important because not only does it block light from getting to the cold side, it actually reflects it away instead of absorbing it into the structure of the spacecraft itself. Yeah. And certain things need to be warm. Like all the communication stuff and all the fuel bottles and things, those need to be warm because they need to be, able to be used, and you can't have a frozen gas tank if you're trying to pump gas into engines, and the radio antennas need to be warm so that they can properly communicate with Earth. And so certain things do need to be warm, but the cold side needs to be really cold. Thank our speaker.